Isaiah, I was talking to a German guy here in Abu Dhabi a couple of days ago, and I said to him, hey, you want to turn back on those nuclear reactors? I said that it's the cleanest, safest, best source of energy in the world. He says, yeah, but it's also the most expensive. First off, is that even true? And if it is, why is it true? Because back in the 70s, nuclear was the cheapest power that humanity has ever produced.
If you have a very non-fundamental view of things, then you'll always just take the price as it is. But the prices have reasons, and those reasons can be complicated. In the case of nuclear, there are some complicated reasons why it's been expensive in the last 20 years. But you can come to understand those reasons and then see why that should be different going forward. So the first thing I'll say is just look at the historical figures, right? Which is exactly what you said before. If nuclear used to be 10 times cheaper, then clearly we're doing something wrong, right? So when we say we need to do nuclear again, we're obviously not talking about copy pasting the 10 failed projects in the Western world that ended up eating tons of money. We're talking about the fundamentals of nuclear, which is that splitting uranium apart makes an enormous amount of heat at a very low cost. And doing that correctly is going to produce a huge amount of very cheap energy. So that's just setting the table of we're not talking about copy pasting failed projects. We're talking about very fundamental stuff. Now, I happen to agree that nuclear as it is very expensive. It's not the most expensive, but it's very expensive. And there's a few reasons for that. The biggest reason is that we're trying to sort of reboot an industry that was suited for 1960s style methods of construction. So in the 1960s, it made a lot of sense to build large civil works projects. And the reason for that is we had a lot of cheap labor and we had the supply chain to do mass scale civil construction. So this is when we were really good at making bridges, making roads, making dams. We were good at the large scale civil works. And nuclear became essentially a large scale civil works thing because that's how we built stuff, right? We were good at building stuff. Nuclear as a matter of physics and design looks really nice the bigger you make it. I would argue actually that even so, I wouldn't make it big. Even if we were really good at doing civil works, I would actually still make it small, but we can talk about why in a second. But anyway, we're trying to build nuclear the same way that we did back when we were really good at making civil works projects. Now, it turns out we're not good at that anymore, right? It's hard for us to make a bridge. It's hard for us to make a road. It's hard for us to make a dam. What we are good at now is manufacturing, right? So if you're going to turn nuclear back on, you're going to turn that switch back on. It will probably not look like the civil infrastructure projects of the 60s anymore. It will look like SpaceX, right? Or it'll look like Tesla, which is essentially manufacturing, right? So we need to, if we're going to turn nuclear back on, if we're going to harness the power of the atom to make cheap energy, we're going to do it in a way that is essentially manufacturing based rather than construction based. And if we do that, it will be very cheap because the fundamentals are there.
Do you think the path of those big, huge traditional nuclear power plants is just gone? Maybe another way to ask this question is, on a gigawatt scale, do you think SMRs or that category of manufacturable small reactors is just going to outpace? Is it going to be 10 times more the output than traditional reactors have today?
Yeah, it will. It just, there's really no way around it. I mean, again, think about the Falcon 9 versus the SLS. Right. So the only way that we sort of rebooted space was to make a smaller rocket that was capable of being manufactured and then just make tons of those. Right. And then that ended up being the only way to get massive amounts of payload to orbit. I think that now what's interesting is that now SpaceX has moved on to Starship, which is even bigger than the SLS. So that's kind of interesting. But you have to start back at that smaller scale because you have to do something that is fast and repeatable and is iterative. And it's very hard to do something fast, repeatable, and iterative when the actual physical thing is huge, right? So you need those small sizes to fit into tooling and to keep the cost down and to keep the speed up. And then once you sort of have the stature of this massive industry that builds hundreds or thousands of the thing, then you can make the size bigger. So I think, the old style nuclear power plants is absolutely going away. If nuclear power plants do get bigger again, it will probably be from one of the small nuclear companies like Valar that gets into a larger form factor because we want to scale more. But I also think that there's like a natural reason for reactors to be smaller, and that reason is safety. So smaller reactors are simply safer, and the reason for that is that I would say there's kind of two main safety challenges in a nuclear reactor, but one of the biggest ones, and the one that was the failure mode of both Fukushima and 3 Mile Island, is that in an emergency scenario, after you shut down the core, you still have decay heat being produced in the isotopes, right? So the reaction has totally stopped, right? There's no more fission occurring. There's no more chain reaction occurring, but you still have heat production, and the heat is being produced in these recently split atoms that are a bunch of different fission fragments, and they're all going down their decay chains and they're producing heat. And you have to be able to get that heat out of the core, right? So passive decay heat removal is what this is called. And in large plants, there's basically diminishing ways to get that heat out of the core passively, and you end up relying on forced cooling. So what that means is you end up relying on the engineering guarantee that coolant continues to move through the core and pull that decay heat out. And in both Fukushima and 3 Mile Island, that engineering system failed. So in 3 Mile Island, it's because there was an explosion in the steam system and the steam escaped, so there's no more coolant. In Fukushima, it was that the backup generators got knocked out by the tsunami. So there's just always reasons why an engineering system might fail. And so to go back to the beginning, why is it that making a larger and larger reactor pushes you toward forced cooling away from passive removal? It's a very simple reason. The surface area of a cylinder scales with the square. The volume of a cylinder scales with the cube. So the bigger your cylinder, the more volume you have inside and less surface area, right, proportionally. And what that means is at the end of the day, there's just a lot of heat production in that cylinder, and you have fewer and fewer ways to get the heat out, right? So if your plan was to essentially use black body radiation as the way to get the heat out, well, you just have so much less surface area now to deal with. If your idea was to use convection, right, so air contacting the surface of the vessel, you just have less surface area to deal with. So I think there's a natural reason for reactors to be smaller. It makes them safer. And the other reason is just that it's easier to produce 10 small things than one big thing in general.
Talk to me about how something that can fit in your back garden can power, 5,000, 10,000 homes or more for a year. How is that, just get a little technical for a minute, how is that even possible?
Yeah. Well, first of all, I would say your garden's going to have to be pretty big to fit this guy back here. This is a real nuclear reactor behind this. Is not a background. I'm inside of my shipping container down here on the factory floor. That thing's it's exactly 20 feet tall, actually, because that's an ISO frame. So it's a little bit bigger, but that's more about the machine itself. I think what's more interesting is the uranium, right? So how is it possible for the uranium to power, cities while being a very small size? The stat that's interesting here is if you used uranium fission to power everything in your life, like your entire life, every single time that you as a human use any power, and I'm not just talking about electricity, I'm talking about just energy in general, right? So getting in a car and driving somewhere, you're using energy. Getting in an airplane and flying to visit grandma, you're using energy. Obviously your lights, but you open up your phone and you use ChatGPT, right? Like every single thing in your life, if you use uranium fission to power that, at the end of your life, you will have used a volume of uranium approximately equal to this cup of coffee, right? Every single day of your life, every single thing that you did, you would use about this much uranium's worth of energy. So uranium is just like this unbelievable cheat code. It's like an energy cheat code left in the world and all around the solar system. And it's here, and you have to be careful how you use it. And using it carefully is essentially the discipline of making nuclear reactors. But it's there. And what's also crazy is that we've done this before, right? Like we did use uranium to power, and we still do, but at an incredibly low cost to power our world back in the 60s and 70s. And so I'm excited because we're going to be going back there again.
I believe we tried nuclear powered rockets at one point. I always remember the Parma Lucky quote, what did we think when we were allowed to think what we wanted? And the 50s and 60s are just ripe with these crazy experiments. Is there one that stands out of like, oh, hey, I wish some entrepreneur would try to bring that back?
Yeah, the nuclear powered rockets is pretty cool. But I think that honestly, Nixon's vision for a nuclear powered society was pretty awesome. And I do think we're heading back that way. Uh, there are a bunch of these realizations about how much energy impacts all of human society and capital and technology. So, what does cheaper energy mean? Well, where does our food come from? Food comes from, plants planted, there's solar power, but then there's also a lot of fertilizer, right? And the fertilizer is generally ammonia based. And that comes from energy, actually, because you have to get the nitrogen out of the air, and then you have to combine the nitrogen with methane, right? And so there's this highly energetic process for producing ammonia, and the ammonia then goes into the different fertilizer stacks. And so there's this interesting feature where cheap energy actually means cheap food, right? And we say cheap energy, we mostly mean natural gas, but it turns out that you can also make ammonia with electrolysis, right? So you electrolyze water, you get hydrogen, combine the hydrogen with nitrogen, you get ammonia. And so there's this idea of like, why don't we make like a ton of nuclear reactors? And they will make grid power, but they'll also make a bunch of other things, right? So they'll make hydrogen, the hydrogen can make ammonia, the ammonia can go to crops, the crops make cheap food. We can also make hydrogen, send it to direct steel reduction, right? Direct iron reduction, make primary steel. That steel is very cheap, can make bridges, right? We can also electrolyze bauxite. That bauxite gives us aluminum. The aluminum helps us make cheap cars and airplanes. We also get gallium and germanium out of that, which help us make cheap microchips, right? So there's this sort of like cohesive, what if we made a bunch of reactors and just obliterated the price of energy, just like drop that thing so low that all of these industries start to become cheaper. And I think it was a very beautiful vision. And this is sort of the progenitor to our gigasite idea. The gigasite is very much this, where you have many reactors laid out in a row. Some of them are making electricity, some of them are making hydrogen, some of them are making process heat. And you have this campus of things that are feeding off of that energy at a very low cost and are complementary and are producing goods at a much lower price than anyone believes is possible today. So that's very exciting.
Just go a little bit deeper into that, because you've called Valar Atomics the anti-SMR SMR company. You take a very unique approach in the gigasite the gigasite strategy, and also producing hydrocarbons. Just go into the strategy and how you came to settle on that.
Yeah, I do call it the anti-SMR SMR company, not because so to back up, what's an SMR? An SMR is a small modular reactor. The idea behind SMRs was that we've made reactors too large, and that's made them very difficult to build. And so let's make them smaller. The problem with SMRs is that there is sort of a reason that reactors were so big. And one of the big reasons is that there's a fixed cost of base cost that you're going to have to get over to do a nuclear project, right? To like do nuclear at all. There's some like minimum floor cost, and you want to, like in economics, if you have a fixed cost, you want to start building lots of revenue on top of the fixed cost so that it becomes a proportionally smaller piece of the overall pie, right? So let's say you have like an auto shop and your rent is $10,000 a month, right? That's a fixed cost. It's not going anywhere. And so you want to do like $100,000 of revenue or $150,000 of revenue to offset your base cost. In nuclear, that base cost is huge because you have so much like environmental work and compliance work around doing nuclear at all, right? So you need to like clear the site. You need to get the community engaged. You need to do environmental studies on it. You need to like get the supply chain and the infrastructure set up. You need to do site security there. You have to figure out the fuel storage. You have to figure out the waste storage, right? So all these different components that come together. Now you're ready to do a nuclear reactor. And so that nuclear reactor better be enormous so that you can recoup all of that fixed cost, right? So this is sort of like why the industry moved that direction. And it's why we keep designing gigantic reactors. It's one of the reasons why we can't keep designing gigantic reactors. So even though the SMR movement was right that you need to make the reactor smaller because it makes the reactor easier to make, it actually made that fixed cost problem worse, right? Where people were looking at like 100 megawatt sites and they're like, well, wait a minute, there's still like $1 billion worth of development costs and project costs before you get to the reactor. And so you sort of made that problem worse. So when I say that Valar is the anti-SMR SMR company, the idea is basically you do make the reactor smaller, but you keep the sites big. And in fact, you make the sites even bigger, right? We want to see 10 gigawatt, 20 gigawatt, 30 gigawatt nuclear sites, but with the unit size very small. And so what you do is you still get to take care of that fixed cost, right? You can have the fixed cost and you get to amortize that, but you're actually able to build the reactors quickly and cheaply. And combining these two things. Now, why hydrocarbons? Hydrocarbons are sort of like how you do this, and you hook the entire system into like the largest power grid in the world, right? So when I talk about something like an energy grid, the first thing that people think of is electricity. But what's interesting is that the electrical grid is one of the smaller grids that we have, right? We actually have much larger grids, and the biggest grid is the hydrocarbon grid. So imagine the pipes and the tanks and the pumping stations all around the world and the ships, right? That grid is enormous. That grid is probably 7 times larger than the electrical grid. And it's global, and it has lower losses over very long distances, and it has storage built in already. So it's a really, really phenomenal piece of energy movement equipment. Let's call it that way. So if you can make hydrocarbons from one of these gigasites, you open up terawatts of demand, right? There are terawatts of hydrocarbon demand, and they become available to you through a hydrocarbon. So that's the reason.
Obviously, bringing on all this new, this new synthetic supply of basically hydrocarbons, what do you think happens to the oil price over the next 20 years?
I think it goes down, and this is not something we've been able to do for like 30 years now, right? Oil has just kind of like capped out, like started high, we worked our way down, we found better ways to drill, better ways to refine, better ways to transport, more efficient uses, and then we kind of tapered, right? And you could say like, well, that's OPEC restricting the supply or, whatever. And yeah, like you find ways to like drop that for a time. And what you discover though is like, we've kind of tapped out how you drill and refine and transport a hydrocarbon. And one of the reasons for that is that the sources keep shifting, right? So like this source is the source today, but over here is the source tomorrow. And so the transportation side of that can't really scale that well. And, you keep having to like pay for CapEx in multiple places to draw the supply from different spots. And then you have like a big refinery, which is a huge amount of CapEx, and then its utilization goes down because actually the oil can't get shipped there anymore because the source changed. So there's all this inefficiency, and we sort of maxed it out, right? Like it's hard to imagine gas becoming, 5 times cheaper than it is today. Mm-hmm. So we really need to switch to something that's like fundamentally different than all those constraints. It's not buying oil. It's not shifting source, right? There's like no reason for a gigasite model of hydrocarbon generation to have source shifting, right? Because you're just purchasing CO2 from either from a nearby coal plant from the air, and you're purchasing water, which is very abundant. So it's different in terms of like you can actually scale transportation CapEx without source shifting, and then you're not purchasing oil. So I think that for the first time in decades, we actually will see hydrocarbon prices trend down, which is very exciting.
Walk me through what these recent executive orders and regulatory changes mean in concrete terms for innovators like Valar, because obviously this has been the big elephant in the room for 50 years now. We've known nuclear was great and safe and all these things, but the roadblocks have been there. So what do these things mean in concrete terms?
Yeah, this is really exciting. I mean, this is like the most important thing that's happened for nuclear in 50 years. I've long believed that the NRC, with all the problems that it has, is actually not the core problem with the nuclear industry. It's a commercial regulator. it doesn't really know what to do with SMRs. It has a bunch of ideas, it has a bunch of thoughts, but it's like never actually been able to turn one on. And the industry's never really been able to turn one on. And there's just sort of like weird chicken and egg situation with it. But actually the problem is that the NRC is mostly concerned with big stuff, right? Like the NRC's job is maintain the existing nuclear fleet, which makes 20% of American electricity, right? And these are gigawatt reactors and they are high stakes, right? Like the NRC deals with the highest stakes stuff in the world. And so when you come to it and say, I have a tiny test reactor, can I turn this on? You're kind of walking up to like a gigantic elephant and you're like a mouse, right? So like there's just sort of a mismatch there. They're dealing with 20% of American electricity generation in gigawatt scale reactors. Like they honestly just don't really have time for this. And this is like the testing and the small scale stuff. And what's interesting is that Congress actually knew this way back in the 60s and 70s and actually afforded for this. And what they did is that they spun the test functions for nuclear into an agency called the ERDA. So it separated out the Atomic Energy Commission into two functions, the NRC, the Nuclear Regulatory Commission for commercial nuclear, and the ERDA for testing. And the whole point of the ERDA was to do exactly what we just said, which is test the small scale stuff. And you were supposed to be able to use that to get through this sort of like early R&D. And then once you're there and you have something serious, then you can go to the NRC and the NRC can say like, all right, now here's how we do that 1,000 times all over the United States. But I think I have always believed there's this natural mismatch going with your small reactor concept to the NRC. So what is the ERDA? You probably never heard of that agency before. It's the Energy Research and Development Agency. And the reason you've never heard of it before is that in 1974, it was renamed to the Department of Energy. So most people don't know this, but the Department of Energy is actually a nuclear reactor test agency. That's literally what it was created for. It was created to test nuclear reactors. And this is so exciting because basically what the executive orders did from the president a couple of months ago is that they sort of executively recommissioned the DOE into doing what Congress originally intended for it to do, which is to test nuclear reactors. So the big headline there's a bunch of stuff in those orders, but the big headline is that the Trump administration has mandated that 3 advanced reactors turn on American soil by July 4th of next year. Incredibly fast timeline, but also incredibly exciting, and we're up for the challenge.
You were one of 10 companies, startups selected for the DOE Reactor pilot program. Just tell me, it's September the 1st today. We're going to switch one on by America's 250th birthday. Of course, Valar Atomics is going to be one of the 3 selected. Tell me we'll be the first. I love it. Yeah, and you can quote me on that.
Yeah, absolutely.
Tell me the pathway from September 1st to July 4th next year. What practically is going to have to happen?
Yeah, we're gonna have to set up a nuclear test site out in Utah. So we're going to be out there in a few days, and we've been out there a bunch, but we're going to have a cool event there, which you'll see shortly. We got to build a nuclear test site. We got to put a reactor on it. We got to fuel it up. We got to turn it on. So I think the biggest thing right now is, just the coordination of all those steps. Like we have it all laid out in front of us, what we need to do. And the biggest thing is like managing all of the tiny, minute details that need to come together, right? It's regulatory. It's, all the little bits and pieces that have to show up on the site at the right time. It's the assembly process. It's making sure, we don't drop a sensitive instrument as we're installing it, right? There's like all these sorts of little things that come together. There's the security and operations. There's the procedures. There's the nuclear safety. There's the health physics, it's all detail work. But that's exciting, right? Because now we have the outlines, we have the plan, and now we just got to go execute.
We have these big headlines of the executive orders and the reactor pilot program and so on and so forth. Are there things like LNT and ALARA and NEPA that can still get in the way, or are these complete carve-outs that kind of allow you to bypass those roadblocks?
Yeah. Thankfully, we've been able to swerve pretty much all of that for this project, right? So because it's under the DOE, and the DOE is just a very unique thing that's really purpose-built for this. We get to swerve all the way, swerve around most of those things. I think the rest of what you just talked about will get resolved, right? So LNT, ALARA, and NEPA will get worked out, and those are NRC problems to get worked out in the next 18 months, essentially. And I think they will. And again, like one of the things I really want people to like take away and understand is that regulators, it's very hard to reform a regulator in theory, right? Like you have to regulate it and you have to reform it in fact and in practice with real projects, right? Because it's too hard to like theoretically tell somebody who's in charge of a regulator, like this rule is wrong. And it's hard for you to even know which rule is wrong. It has to be tested against real things in the real world, right? And when you have a real project in the real world that's being held up, or you can say like, hey, this reactor turned on under the DOE. How long would this have taken if it had to go through an NRC process? And what would the result have been? And you can compare and contrast and you can say, okay, like, yeah, clearly something's broken here. We need to fix it to be able to make that project run, right? You can really only regulate things that exist, right? You can't regulate things in theory. You can't regulate like principles of nature. Regulators can regulate existing technology, but when you're innovating and you're moving fast, you have to have something that's very dynamic. And then once that thing exists, then you can kind of take it to a more stable regulatory regime. So all of these things will be worked out, but they will be worked out through building. They'll be worked out through these types of projects happening on the ground. The NRC can look at them and say, okay, well, clearly we need that piece of flexibility because look how fast this thing actually went, right? And we would be the bottleneck there. It's very exciting. It's going to be a great time.
Amazing. You've said that engineering is now the bottleneck as opposed to regulation, which it has been for 50 years. Of course, a good problem to have. What's the hardest technical nut that you still have to crack?
So for us, we made this a little bit easier for ourselves because we picked a really simple reactor. But I would actually say probably power conversion. Like the reactor architecture that we picked is so simple. It's a really, really bulletproof reactor, incredibly high safety margin, very easy to build, really easy to construct, huge supply chain. And so really we're like sort of in the ancillary systems now in terms of like where the engineering difficulty is.
You have this vision to make nuclear the cheapest power in the world. I've talked to some other, small modular reactor, micro reactor startups that kind of frame it as premium power. Yep. What do you know that they don't, or what are you going to achieve that they can't?
Production rate. We're just going to make so many of these things. We're going to. So there's like two things. One is if your reactor is too small, then production rate won't solve it. Like you have to have the right size, right? We're going to make a 25 megawatt reactor, and at 25 megawatts, mass production will make that the cheapest energy on Earth. If your reactor's a lot smaller than that, yeah, it's kind of hard to, production rate will help it a little bit, but you're probably not going to get cheaper than nat gas. So if you have like a 1 to 5 megawatt reactor, let's say, it's hard to see the production rate actually helping that. But at 25, like absolutely, we're just going to make so many of these things, and it's going to be the cheapest energy on Earth.
I've also heard you say it's either China, Russia, or Valar. How do you size up? You don't have to mention names, but how do you size up a lot of the other US competitors? And just how do you? I was doing a dive into them. There's at least 15 or 16 of them that seemingly on the frontier working on real technology. Just how do you think about all the competitors?
Yeah, there's a lot of people. Talking about competitors is really hard because they're all so different, right? And I could talk about any one of them and have something very specific to say, but talking about them as a field is very difficult. The most, general thing that I'll say is that let's just separate it to two classes. Startups that have been around for a while and brand new ones. So on the brand new ones, I'll say, we'll see. Right, like I have high confidence that Valar is going to win and it's going to take the whole market. There will be other pieces, but like we'll be the runaway winner. But we'll see, right? Like these guys are also taking a crack at it and moving quick, and we respect that. The other bucket is the startups that have been around for a while, and I would say that they missed something that's very, very important, which is you simply can't design a nuclear reactor on paper. Like, you just can't make technical progress in theory. The only way that genuinely hard technologies have ever come into the world is through building them. Like, you just have to build it. You have to turn it on. You have to test it. You have to figure out what's leaking. You have to figure out what won't tighten properly. You have to figure out which systems won't integrate. You have to figure out which protocols won't talk to each other. Like, that is actually the hard part. And if you have gone for 5 or 10 or 15 years on paper without tackling any of those problems, you misunderstood what technology development is. And so, yeah, I hope you figure it out soon.
You mentioned about the protocols. Just, we often think about nuclear as hardware. How much software goes into a modern nuclear microreactor?
Yeah, there's a ton of software. I mean, there's software all over this thing, and there's also like electronics, right? So there's like analog systems and there's digital systems, and the digital systems have some software, but there's a huge amount of both electrical engineering and software engineering that goes into these. Now, Valor in particular, I would say that we are cautious about overspending on software, and so we built this entire system behind us here without a single software engineer on the team. We have a lot of smart people, and those smart people happen to know software, right? I wrote a fair bit myself as I had to, but like we don't, we built pretty much all this and operated it under pressure without having like a software team. And this is one of these things that like scares VCs, and like VCs want to believe that everything they invest in is like actually a software company. This is wrong. The most exciting companies in hard tech are not software companies. They're not like, people have this insane idea, like genuinely insane idea. If you are a VC and this is in your head, please come like text me or call me and I will dispel you of this notion.
You need the Men in Black pen.
Yeah, totally. But like, if you have this in your head, like remove it or call me and I'll remove it for you. SpaceX is not a rocket company with software. That's not what it is. Like they have this crazy idea that like SpaceX is like this software company that happens to use rockets as a moat or something like that. But actually it's a software company. That is not true. Even a tiny bit true. Like obviously software is involved in what they're doing, but that is not what's going on at SpaceX. The reason that SpaceX is successful is similar to why certain software companies are successful, but the fundamentals is that they execute on an incredibly hard technology in a way that produces a huge amount of leverage, and then they apply that leverage to massive margins on the market, right? And how did they become masters at that technology? The same way that all great technologists do, which is that they push forward toward the efficient edge of known information at a faster rate than anybody else, and then they operationalize that information, right? So what I'm talking about is like there's a theoretical way of how you produce a Keralox rocket motor, and you have to push out to that efficient edge at all times and then operationalize that knowledge. And if you are doing that slower, SpaceX will beat you. And that is exactly what has happened to everybody. And that's the same thing that's going on here at Valor. And of course you use software, but I'd like to point out that the G-fold algorithm is from the 1950s and it landed us on the moon, right? So like we know how to land rockets with software, but it's the operationalization of that and the experimentation and the actual, launching and landing and launching and landing and launching and blowing up and then launching and landing. Like that's the process that pushes SpaceX forward. And that's really what hard tech is kind of all about. And that's what we're all trying to do.
We talked about the DOE, testbed carve-outs. How do you think about the DoD and all this? They've kind of emerged as another one of these, kind of loopholes, let's say.
Yeah. So if you read the executive orders on the DoD part of this, you'll notice that it basically says that the DOE and the DoD will collaborate to figure out how to move forward here, which I think is an awesome start. Eventually, I believe that the DoD will sort of have more than so right now, like the DoD does run its own reactors underneath underneath naval nuclear.
Yep.
And I think that over time, DoD will figure out how to do that again in other places. It'll figure out how to do that for Army. It'll figure out how to do that for Marines. It'll figure out how to do that for Air Force. And they're currently trying to figure that out. And basically, the executive orders tell DoD, have DOE help you do that by 2028, which is super exciting. So we're going to see a lot more of it. That's all I'll say for now.
I've heard you call nuclear waste the safest form of trash humanity has ever invented. Why is there such a disconnect between public perception and the actual reality, and how do we close that gap?
Part of it is the fact that, there's two things. Like, one is I think that there were specific pieces of propaganda that were intentionally disseminated. I believe that our rivals throughout various times in history have tried to dissuade the American public from nuclear because it is such a powerful thing that, that we can make metal cheaper and we can make power cheaper and we can do AI cheaper and all these sorts of things. So I think that we have sort of been like intentionally misled away from it, exactly like Germany was in the last 5 to 10 years. Russia, like, very explicitly convinced the German public and German politicians that nuclear was bad, so that they would stop nuclear and they'd turn their plants off and would become more dependent on Russian gas. This is a known fact that this happened. So I think there's some of that. There's also just the fact that the media pieces that portrayed nuclear have been very focused on atomic weapons, right? If you like Google nuclear, there's like kind of two categories of things that come up, but like nuclear bombs are always like up there. And so there's just sort of like some co-branding that's a problem there. It's very interesting that fusion didn't like catch this as much. I'm not sure why that is. And it's like worth considering, like, why fusion didn't really get coupled into that as much. Like, people love fusion. If you talk about like, oh, fusion, like fusion's coming, like people aren't like, oh, atomic bombs, even though atomic bombs are all basically fusion bombs at this point. So that is kind of ironic that it just didn't really cross over psychologically. But it's like a branding problem. But I think what's interesting is that the information age has like totally obliterated that. Like, if you look at my generation, who like reads stuff and reads, Googles things and like watches podcasts about people talking about stuff and just has a ton of information about this, they are extremely pro-nuclear, right? So the generation that got all of their information from, it's like a centralized source, which is like TV and newspapers, are either don't like nuclear or like sort of against it. Our generation, which is like democratized access to information, loves nuclear. Yeah, there's a huge irreversibility to that. Like, you just can't put that cat back in the bag because everybody just knows about it now. Like, if you were to try to quickly spread an anti-nuclear narrative globally, it would be very difficult, right? The information is just very sticky. So that's exciting. I think it's a really fun time to be building nuclear.
It's almost like we've got the antibodies. We've got the antibodies
yes.
to the anti-nuclear
argument. That's actually a great point. And I think that Fukushima actually contains some of those antibodies. Basically there was this nuclear incident in Japan, and the Japanese response to that was like immediate, and it was, I would say, like massively overheated, right? Like they evacuated, I think, 100,000 people. And it turned out that the evacuation effort killed more people than the event, which was 0, right? So the event didn't kill anybody. And the evacuation effort did kill people. And so there was this like, okay, our reaction to the thing was worse than the thing. And that actually created some antibodies of like, did we as a society just like catch this weird bug about nuclear that, kind of made us act irrationally. And so I think it's exciting that we sort of seem to move beyond that. Or we're sort of like cautious in the other direction now. We're like cautious about nuclear scares, which is great.
I'd love to get a little technical for a moment to just walk through how your reactors Ward 0 and then Ward 1 work. You mentioned passively cooled earlier. Why can't they melt down? And just talk me through the design of the reactor, the design choices, I guess. Like, I believe that the fuel is triso, the moderator is graphite, and the coolant is helium. Just walk through all those design choices, basically.
Yeah, you nailed it. So those three design choices lead to a very, very safe nuclear reactor. So triso fuel, graphite moderation, helium coolant. This is an excellent safety stack for a nuclear reactor. Triso is kind of where it starts. Triso is this incredibly strong form of nuclear fuel that is capable of reaching high accident temperatures. That's super important. It basically there are like a couple of different features of a nuclear design when it comes to safety, and one of them is called containment. So containment is the barrier between the fission products, right, which are highly radioactive and toxic, and the outside world, right? So you have to have a physical barrier between fission products and the outside world. In a traditional nuclear plant, that physical barrier is a big concrete dome, right? So if you've ever driven by a nuclear plant, you've probably seen this like big old concrete structure. That's called a containment dome. And it's literally just placing a ton of strong mass between the world and fission products. Now, this is generally a sphere because spheres are a very strong, materially efficient structure, right? But the one problem with a containment dome is that they're huge and they're expensive and they're still not that strong. Like they're good, but you could get through them, right? Now, the reason for that is that they're big. And it turns out that the bigger a sphere is, the worse it is. So I'll say this again, the larger a sphere is, the worse it is at being strong, right? So the strength of a sphere scales inversely with its diameter. So if you have a very, very tiny sphere, that sphere, it can be extremely strong per shell thickness. And so triso basically like takes that idea. So the idea is like, what if you just kept making the containment dome smaller and smaller? It would get stronger and stronger. And triso basically takes that idea to its like fundamental logical conclusion, which is that what if the containment dome is actually like that big? And that's what triso is. So triso is these tiny little beads of uranium, and they are wrapped in these layers of very, very hard ceramics. And those ceramics make up containment. And it turns out that once you scale it down to that tiny size, that ceramic sphere is actually hundreds of times stronger than a gigantic, 9-foot thick concrete rebar reinforced high density concrete dome, which is really awesome. So that's kind of where the safety starts. Now, the other thing that's super important about this is because it's a ceramic, it has high temperature resistance. So in an accident scenario, the core can reach a very high temperature without releasing any fission products. And in triso, that's somewhere around 1600 degrees Celsius, which is really hot. And the nice thing about that temperature is that if you allow the core to get very hot, you actually increase the ways that heat can escape, or you increase the volumes at which that heat can escape. So for instance, black body radiation. So black body radiation, this is basically just hot things radiating heat, right? And black body radiation scales with the fourth power of temperature, right? So if you double the temperature of an object, the amount of heat that it is emitting will actually go up by 16x.
Wow.
Right? So it's not linear, it's to the fourth power. And so what that means is if your reactor is tolerant of higher and higher temperatures, it is actually able to emit more and more energy, in an accident scenario. The final one, the next one is graphite. So the fact that you use graphite as a moderator is really great. Graphite has a very strong negative thermal feedback for reactivity. And so what that means is as the temperature of the core rises, the reactivity of the core tapers and then eventually drops, right? So what that means is it's incapable of nuclear runaway, right? So it's incapable of a runaway state where you have criticality and then your criticality actually, your KF continues to increase and then you have, sort of a neutron population that's out of control. It's actually incapable of this. And that's because you have this really tight feedback between temperature and reactivity. This is a nuclear physics concept. I could explain it, but it takes a while. The other thing that's really interesting, though, about graphite is that it has high thermal inertia. And this goes back to what we talked about before in the decay heat. So when you shut the reactor down, your TRISO is still producing heat, a lot lower than when it was when the nuclear reaction was active, but it's still producing heat. And that heat needs to go somewhere. And fundamentally, you want the heat to get outside of the core. But even before it gets outside of the core, graphite has really high thermal inertia, right? So think about inertia, right? So imagine you have like a big block of steel floating in space and you hit it with a hammer, right? You whack it with a hammer, it doesn't move that much, right? It starts moving, but like not that much. So now apply that idea to heat, right? So if you have something with high thermal inertia, you can hit it with a ton of heat and it won't heat up that much, right? So it will absorb a lot of that thermal energy without increasing its temperature too much. So this is what graphite does. It just is like a giant heat battery. And so post shutdown, that TRISO can transmit a ton of its heat to the graphite without the graphite reaching dangerous temperatures. And then the last thing is that the graphite itself can also reach enormous temperatures without sublimating. It can get well beyond 2,500 degrees Celsius. Wow. The final thing, and sorry, I know you asked me like a 30-second question. I gave you a 5-minute answer. My apologies. This is dangerous to ask me about the technical questions. The last thing is that we use helium as the coolant. Helium is a great coolant. It's invisible to neutrons. What that means is that it will not capture neutrons and become radioactive. And this is unlike water, right? So water in a nuclear reactor will become radioactive. And so if you have a leak in the system, you have radioactive leakage. You have to treat the water as waste, right? So it's like, this is in working fluid. Water in a reactor is nuclear waste. And so helium is just a lot cleaner. It's a lot safer. Also, the biggest thing about it is that helium starts a gas and stays a gas. And so you don't have phase change that you're worried about inside the nuclear system. So in a normal nuclear reactor, you have water as the coolant, and you're always sort of like thinking about phase change, meaning what happens if all of that water suddenly becomes steam, right? And when water goes from liquid to gas, the pressure of it increases by about 1,500 times, right? So water to gas is a 1,500x pressure spike. And that's a steam explosion, right? So that's what has happened in many steam-based systems. Helium starts a gas, stays a gas. It's a noble gas, which means that temperature and pressure are directly related, right? So you're never going to have a 1,500x pressure spike. If the temperature doubles, your pressure doubles, and that's well within the bounds of like being able to engineer a system. So anyway, there's like 70 years worth of like thinking into how to design a really safe nuclear reactor. I do believe HTGRs are kind of the best in the world at this. And that allows us to make many of them and operate them safely.
As we gear towards closing here, Isaiah, I thought we could play some devil's advocate. So I'm going to put out some things that someone listening to this conversation, some questions they might have, some pushbacks. So the first is, hey, I'm so worried about these small modular reactors. What if a terrorist gets their hands on them? Can they turn it into a nuclear weapon?
Yeah, so TRISO is really the best defense against this. You can make other reactor architecture safe as well. I'm not saying that TRISO is the only type of safe small reactor, but TRISO gives you a ton of bang for your buck here. TRISO is incredibly difficult to reprocess. There, again, we talked about these like incredibly strong, like mini containment domes. Turns out they're like unbelievably hard to access. And this is one of the reasons that they were invented, actually, is to prevent, this is called non-proliferation. Basically, how do you prevent the wrong people from accessing nuclear material? Actually, I was talking to a guy who works in nuclear reprocessing. And I was like, have you guys tried to reprocess any TRISO? And he's like, well, we ran it through the grinder machine and it broke our grinder machine. And so I was like, okay, nice. That's good to know. Basically, it would be probably easier to try to steal any other type of reactor or like try to breed it yourself or something like that than to try to actually access the TRISO out of a nuclear reactor. So there are things to think about, lots of security that we think about, but it's a really annoying form factor to try to do something bad with.
If SMRs are so great, why hasn't China built 100 of them already?
They're getting there. Yeah, give them a little bit of time. I mean, China's new at this, right? Like China's new at the nuclear game, and they're currently figuring it out. But I mean, China has turned on two of the type of reactors standing behind me right here. The first one was, I think, 5 years ago. The second one was, sorry, 5 years ago, 4 years ago, and 2 years ago. Yeah, I'm going to get those dates wrong. Someone's going to correct me. But yeah, like give them time. They're working on it. And we got to work faster.
For sure. We want to bring these learning curves to SMRs. We want to pump out the reactors, make them, faster, cheaper, safer, all those things. At what point do learning curves kick in? It's maybe not going from 1 to 4. How many of these things do we need to produce to get those learning curves?
Yeah, I think the number is probably around 5, like 5. But I would just point out, like, if you make your reactor really small, 5 is something you can do in a year, right? If you make your reactor gigantic, 5 is like decades, right? So this is just one of the basic reasons that you make the reactor small. It's like you want to make it small enough that you can do it a lot, and doing it a lot teaches you a lot, and you move that idiot index down closer to 0.
NuScale's project.
Okay.
Yes. Yeah. NuScale's project after costs ballooned. Why is Valar Atomics different?
Our reactor's a lot smaller, and also we build the reactor and test it and run it and like get to know it before we put uranium in it. And so, but I think the biggest thing is just like our reactor is a lot smaller. It's a lot easier. We can move a lot faster, and we don't try to skip all the steps, right? I think one of the big failure modes that people have experienced in nuclear is that they really so badly want to get to commercialization. They and their investors want them to, and everybody wants them to like get to selling commercial reactors, that they always try to skip everything that leads up to that, right? But again, with SpaceX, like they had to build the Falcon 1 first, and they had to launch it and blew it up and blew it up and blew it up. And then it finally flew, and then they could fly the Falcon 9, and it blew up, and then flew it again and it blew up, and then they flew it. And then it had to figure out how to land itself in a crash, and try to land itself in a crash. And like, you have to get through those things. And no amount of design will get you there. You simply cannot do it. Like, you could give Elon and SpaceX $50 billion and 50 years to try to build what they built, and you wouldn't do it. It just doesn't work that way. And you would have spent $50 billion in 50 years. So the only way that you actually get to commercialization is you have to test the systems, and you have to get to know the nuts and the bolts. And so like that's what we're going to do.
2 closing questions for you. What truth do you believe about nuclear that most of your peers in the industry think is crazy?
It will be the cheapest source of energy in the world in the next couple of years.
And I think both of us are over the 2.1 threshold for kids. Leave us with a dose of optimism. Why should kids be optimistic about the next 10, 20 years? Give them, some optimism, some agency.
I mean, it's going to be so exciting, dude. Like, I love playing Minecraft.
Where do you find the time?
Yeah, no, I don't really play anymore. I used to play. There's really only 2 games that I've like seriously played. Minecraft and Counter-Strike, and unfortunately, I probably have like 3,500 hours in Counter-Strike. Since starting Valar Atomics, I probably have 8. So that's kind of fallen off. But like, one of the things that I noticed was when I was working on other companies and other things, like I would always keep coming back and playing Minecraft. And since starting Valor, there have been a couple times when I played it with friends, but like I realized that I'm playing Minecraft in real life, and that is just so much better. It's harder, and like you have to wait longer for the reward, but like that's what we're doing now. We're playing like Minecraft alpha in real life right now, right? Like we're not really playing it. You have to wait a long time. There's too much like nonsense you're dealing with. The supply chains aren't really there. I think one of the reasons that people love software and that software like sort of like snipes everybody who's smart into working on it is because software, you really are playing Minecraft, right? Like what do I mean by that? I mean that you're like creatively working in this open world where the tools and ingredients are there and they're composable, and you can like make compositions of things that have new functionality, and then you compose other things on top of that and compose other things on top of that, and you're like building this world. Software's like that today. And in Minecraft is this game where the physical world works in a software-like fashion. And it's composable and it has components to it. And you can quickly compose worlds. But we're going there, right? Like that's happening in the physical world. It's happening through advanced manufacturing. It's happening through energy being cheaper. It's happening through robotics. It's happening through like more and more precise engineering and nanotechnology and like all of the things that people around the world are working on to make the physical world more addressable and more componentized and more composable is making the physical world more like Minecraft.
Yeah, no, besides nuclear and energy, what innovation, what breakthrough are you most excited about in that Minecraft future?
Yeah. So there's really only three things that I think are like extremely important to be working on: energy, intelligence, and dexterity. Right. So these are the three things that make up everything. Energy is really obvious. Intelligence, really obvious. Dexterity, maybe the least obvious right now. But we need the ability to like physically manipulate the world with detail, right? So examples of dexterity are like everything from a robot arm to a manufacturing line, right? The manufacturing line is actually an example of dexterity, right? It's like a set of machines that manipulate matter into a desired shape. So like getting better at all three of those things, energy production, intelligence, and dexterity, are what are pushing those forward. So I think the thing that I'm like very excited about right now is intelligence and dexterity starting to work together. And it needs big improvements on both. Like intelligence needs to get a lot better. Dexterity needs to get a lot more flexible. And I don't really think it's a humanoid, although we can talk about that. Like I actually think that humanoids will be a very large business, but not really what people imagine they'll be for. Like I don't think you're going to see like factory floors crawling with humanoids. So there's something else that needs to be made, which is more generalizable, and it will probably not look like a human, but it is capable of manipulating matter, and that intelligence can be applied to it, and it needs energy, and I'll provide the energy, and then we all play Minecraft, and it'll be super fun.
Isaiah, thank you so much for your time. This has been fascinating. Where can people find more out about what you do, what Valar Atomics does? You can follow me on Twitter or x.com, Isaiah_P_Taylor. You can also go to valaratomics.com, VALAR atomics.com. And we will all be following along, as Valar Atomics is the first startup to turn on a new nuclear reactor on US soil. Thanks so much for your time. We'll talk soon.